Bow your heads, please.
Heavenly Father, thank you for this day. I thank you that we're all here safe, and I pray that today will be a smooth day, and that we'll understand what we need to cover, and that we'll all give you grades on our tests. Amen.
Amen. Thank you, sir. We are in the gas chapter. Chemistry is not complete without studying gases, because a lot of what we learn about chemistry came from the people that were working with the gases. And so the first thing he has to define for us is pressure. And we have pressure equals force divided by area. And I probably haven't told you this before, maybe. But for me, you guys already know I'm a little twisted. What definition got me through as far as thinking through things. So for test purposes, you definitely need to know that pressure is force divided by area. Remember in physical science you learned that atmospheric pressure was 14.7 pounds per square inch, right? Pounds is a force, per square inch is an area. Okay, so that's what pressure is. And you already read that we can measure that in atmospheres, torr, millimeters of mercury. Those are all the different ways now that we measure. And once again, you learned that in physical science. We learned all of those in physical science, that those were the different ways that you could actually measure pressure. But what idea will help us think through things as we go through dealing with gases is that pressure is the number of collisions. The number of collisions you have a gas making with whatever container or whatever else is around, that is how I equate pressure. And let's think about this for a minute here. Okay, I'm going to tell you that gases, we're going to think about bumper cars, because bumper cars help us to think through gases. Has everybody here at least seen a bumper car ring in action?
Yes.
Okay. No? Yes? Okay. So just in case there's somebody out there that hasn't seen a bumper car ring, it's a ring that's at the fair, and they have a bunch of these little cars, and everybody gets in it, and they run around banging into each other, thus bumper cars. Okay. We're all on the same page. Now, if you think of the gas molecules as the bumper cars, those are the molecules. You think of the ring as the volume of the gas that it's in, because your gas molecules are the bumper cars, and the size of the ring gives you your volume. What would the speed of the bumper cars be equal to in this whole thing? Think about it. How do we measure the speed of a molecule? In temperature. Right? The faster a molecule goes, do you remember this from physical science? The faster a molecule goes, the higher the temperature. The slower the molecule goes, the lower the temperature. So the speed of the bumper cars equals the temperature. You got the picture so far? Okay. Personally, this helps me to think through these concepts because I can relate to bumper cars. Been there, done that. Okay? Gotten a few whiplashes from it, you know, but yes. So, we're told about Blaise Pascal, and that he did a lot of work with pressure. And remember that in metric system, a Newton is a force. And if we have newtons per meter squared, then we have a Pascal. But we don't tend to use that pressure measurement very often because it's a very small pressure measurement. So the one that you more often see is atmospheres. And look at this, a regular, sea level of 14.7 pounds per square inch is one atmosphere of pressure at sea level. It's 101,325 pascals. That is a very small pressure measurement, isn't it? Okay, so that's why we tend not to use it very often. It's easier to write 1 atmosphere. It's just easier to use. And I love how I keep saying chemists are lazy. Let's be honest, people are lazy in general. So that's why, we're going to use the easiest one we can. He points out that we use barometers to actually measure pressure. You remember doing this in physical science where we actually made a very crude barometer by putting water into a little container and putting a candle in it with the glass over the top, and we pulled the water in by burning off the oxygen, and the atmospheric pressure was less inside and more outside, and it pushes the water into the glass. Very crude barometer. But basically normal barometers use mercury because it seems to me that the water would go up something like 33 feet because it's so light compared to mercury, and that's why it just was not feasible to use water, plus it evaporates. So they use mercury in barometers, which is much heavier, and when you're at atmospheric pressure, which is 1 atmosphere, the mercury will move up in the barometer 39.9 inches of mercury or 760 millimeters of mercury. Now I notice he only mentions the millimeters of mercury here, and Hg is mercury. So when you see mmHg, it's talking about millimeters of mercury, and that's how high up it pushes it. So it tells you here that 1 atmosphere equals 760 torr, which actually also equals 760 millimeters of mercury. It's in physical science that you have to know that that's 39.9 inches of mercury. So we'll just let that go for right now, okay? All right, so on 291, the comprehension check, it says a barometer reads 750.1 torr. How many atmospheres is that? So you would just do a conversion. Do you need to see the conversion? I didn't think so. You guys should be able to do that. You just do a conversion. You do a times line, put torr on the bottom, atmospheres on the top. Atmospheres get 1, torr gets 760. You're going to answer in 4 significant figures because that's what you started with. And we're going to consider that the 1 atmosphere has an infinite number of significant figures and the 760 has an infinite number of significant figures. So our answer would be 0.9870 atmospheres. So that it has 4 significant figures. Okay, are we good on that? We're going to go on. Boyle's law, and it gives you the really interesting painting of Boyle. This is back when they wore wigs, which I find rather distressing, but that's okay. Anyway, just always freaks me out. Robert Boyle lived in the mid-1600s. This was at a time when chemistry was considered alchemy. And alchemy was this idea, if you ever haven't studied scientific history, it's rather eye-opening to study, trust me. Oh, and the history of medicine, you should do that one sometime. That's like gruesome. But anyway, alchemy originally was the idea that they could take lead or other cheap metals and that they could convert them into gold. And that was like the whole drive of alchemy, was to try to take things that were not precious and make them into something that was worth money, that was precious. And so Robert Boyle is the one that actually moved chemistry out of the alchemy stage by saying, well, wow, maybe we can use chemistry to learn things about creation, and maybe it's actually a real science. And so that's why he's considered the father of chemistry, Robert Boyle. And it's interesting that he pointed out that he was a Christian and that he started Boyle's lectures in 1692, which were a series of lectures to provide evidence for the truth of Christianity. I had never heard this before. And that they're still given. They're not given every year, but they are still given today. So I found that rather interesting. Anyway, we have an experiment on the next page. So on 10.1, and I'm going to do this up here and hopefully not hyperventilate and die. And you're going to be my mirror because you're supposed to do this in a mirror so you can watch what's happening. Can you see through, let's pull that off. Can you see through my jar? We're supposed to go, right? So we're supposed to just put a little bit of air in our balloon. We're supposed to tie it off, which is always difficult. There we go. All right. Everybody see? You got to get where you can actually see this. Let's get you in here. Come on. Thank you. There it is. I had a student kind enough to make me the donut earlier. So, no, it wasn't him. No, it was one of my Florida science students, because he did it while I was listening for class. I figured he could multitask. He's a real sharp guy. Anyway, let's see if I can. I got to have a seal here. Yeah, it's got to have a seal or it won't work. Let's see if this works. Watch the balloon, please. That's what you're supposed to be watching, okay? Are you seeing any change? Is it getting bigger? Yeah. That's what it's supposed to do. Thank God. Oh, it is getting a little bigger, isn't it? Ugh, I can taste the Play-Doh.
Play-Doh?
All right, did everybody see it? Good, I'm done. Okay. And I even ordered this nifty little hand vacuum pump. See this? Woohoo! Aren't we cool? Okay, so we have our balloon. Everybody sees the size of the little pink balloon. Yes, we have our Play-Doh donut, which actually functions as a gasket for those of you that are mechanical. A Play-Doh nut, that's it. I like it, Joe. And then we have our little funnel, which we're gonna really kind of try to press it down here so that the Play-Doh nut actually functions as a gasket, which means it should be airtight, right? So I'll just kind of wrap that around there a little bit. And then I'm going to try to do this without squishing the donut too badly. Okay. Nope, it's all good. I'll just hold it there, what do you think? Okay, and then I'm going to pull the air out of it. Oh, I think I released it, hang on, let's try that. I see something happening, but do you guys see anything happening yet? Here, can you see? I know what I'm seeing happening. The donut's getting squashed.
It's harder to see because the top is falling on the top.
Ah, let me turn it around. There, I'll move this way. So we
Do
can
you want
see.
me to hold it up for you?
No. Can you guys see what's happening with the balloon? Everybody just needs to see the balloon. I'm sorry about the donut going sideways. Okay, does everybody see what's happening with the balloon? Okay, the balloon got larger. I'm going to release, try, maybe not. Hey, what did we see there? What we were supposed to see is that when I sucked on it, it actually lowered the pressure in the jar, and therefore the balloon started to inflate. And he pointed out that if we had a vacuum pump and we actually vacuumed the air out of the container with a balloon in it, the balloon would actually inflate because the lower pressure inside the vessel allows the balloon, the pressure that's in the balloon, to actually, the particles to actually expand out. Okay? And so with that, we have Boyle's law, which is at constant temperature, pressure and volume are inversely proportional to one another. At constant temperature, pressure and volume. You know what? For Boyle's law, you can just write P1 V1 equals P2 V2. To me, that's less confusing. Okay. Now, with that in mind, let's think about that for a minute. So Boyle's law, you will need to know these for your test. I'm sorry. Boyle's law is P1 V1 equals P2 V2. Now here, we're keeping the speed of the bumper cars the same. Temperature is held constant, right? So what we see here is that if I have speed's the same. Pressure is the collisions. Let's say I increase the collisions. What has to happen to the volume of the ring if the speed remains the same? To have more collisions in my bumper car ring and have the same speed, what do I have to do to the size of the ring? Shrink it. I want more collisions, but I have the same speed and I want more collisions, I would have to shrink the size of the ring, wouldn't I? Right? So when one goes up, the other has to come down. Let's go the opposite way. Let's say I want less collisions, same speed of my bumper cars, but less collisions. I need a bigger ring so that there's less chance of hitting each other. Does that make sense to everybody? I know I'm probably the only chemistry teacher in the world that teaches gases with bumper cars, but it got me all the way through college and it worked every time. Okay, so bumper cars works for this, all right? So what we see, that's why they're inversely proportional. As one goes up, the other comes down. But that to me is like, makes my brain want to scream. So just remember P1 V1 equals P2 V2. Okay, P1 and V1 are the first scenario, and P2 and V2 are the second scenario. So if you alter something, everything's got to shift so that it ends up where they're equal to one another. Okay, that is Boyle's law. Now, he applies that on page 294 to how we breathe. And that's important. And actually, if you take the Apology of Anatomy, they require you to have chemistry before you take it. But this is kind of like the only reason you need it. So I personally don't see the need to suffer through the entire course of chemistry just to take anatomy. That's just me personally. But it's this idea, our diaphragm is the muscle underneath our lungs. And so when it contracts, tightens up, it gives more space for our lungs, and therefore we have less pressure in here because there's more volume, therefore less pressure, so the air moves in to our lungs. When the diaphragm relaxes, so it becomes like this again, it makes the cavity smaller, and therefore it then pushes the air back out. okay, because you have less volume and therefore the pressure increases and it pushes the air back out. So that's the way our lungs work. Excuse me. Then we get to Charles' law. And Charles lived in the 1800s, and it tells us here that Joseph Louis, so I think it's Louis, Joseph Louis Gay Lussac actually is the one that did this work, but he credited Charles because Jacques Charles did the original discovery. And Charles, though, himself apparently was a balloonist, and that's why gases were important to him. And he and his two brothers designed the first hydrogen balloon that people flew through the air in, and so that's kind of interesting. And so that's why they discovered a lot about gas laws. Now, this one could be dicey, so let's try this together. What do you say? Here I have a ball jar. The lid is going to function as our plate over the top of the ball jar, okay? I'm using a ball jar because we have to pour boiling water into it, and I don't want it to shatter or explode, which I've done all of those things before, can you tell? Okay, I brought this from yesterday because I worked very hard to get a balloon that actually fit into there, but wasn't too big. And so then we are supposed to float the balloon on some water. So we float the balloon on the water, and I actually have this jar marked, at least I did yesterday. I don't think I do anymore. I used a Sharpie too. Anyway, let's float the balloon. There's actually, well, let's see. You guys read the lab. Am I doing anything I'm not supposed to be doing? Here, I've got a little room between the top and the bottom. I do not have tape, but you know what? I'm just going to use one of these Sharpies. It's not permanent, but it'll do. I am supposed to mark where the water level is, correct?
I have a Sharpie.
It's okay. This will work.
Okay.
This will work.
Also,
Hey.
the balloon's supposed to be touching the plate, it says.
Oh, it's supposed to be touching the plate.
Mm-hmm.
We have to increase our water level. Thank you very much, Boyle. Appreciate it. All right, so it's got to, I'm going to kind of try to ditch the stem here. There we go. So we need the water level to be such that it will touch the plate. That may be a little too much, huh? Okay. Let's pour a little out. Okay. That looks about right, right? Okay. So we're supposed to mark our water level. Here we go. Okay. Then we are supposed to, pour this water in here. Yes?
You're supposed to mark the water level after you take the balloon out because,
Oh, that makes sense because of the volume. Thank you, Joe. Okay, so you know what? I pulled the balloon out. Aren't we glad I used erasable marker? Okay. Oh, it is exactly the same level as yesterday. The reason I know that is it's got a milliliter ml on here, and it was right level with the L, and it is now too. There we go. Okay. Now, aren't we supposed to put this balloon in the freezer?
Yeah.
Okay. So, Mrs. Moody, I'm going to hand you the balloon, and just stick it in the first freezer you come to. Okay, please. And we are going to take the water. Plus, we're supposed to add a little water to it, aren't we? In case it boils off, right? And we're going to boil that water. Okay. Now, while we're doing that, this is my plate, like I said. Thanks for your help. That's a good point because the displacement of the balloon changes the water level, so that's really good. Appreciate that. Okay. Below that, we have Charles' law, and we're told at constant pressure, temperature and volume are directly proportional to one another. So how that's expressed mathematically is volume 1 over temperature 1 equals volume 2 over temperature 2. And here in this experiment, we're supposed to be keeping the pressure constant by keeping the plate on the top of the whole thing, or the lid in this case, on the top of the whole thing. That will apparently provide what we need for pressure. And we're going to see this in a minute, but I bet you can guess what's going to happen when I put the balloon in with the boiling water. What's going to happen? Actually, it didn't pop, which really surprised us, because we were expecting it to pop. But what did this balloon do? It grows, it expands. And so then it presses on the plate or lid above it. And actually, in this case, it'll push it off. You know, it'll definitely push it up. And so what we're seeing there is with an increase in temperature, we have to have an increase in volume. Whereas with a decrease in temperature, we have a decrease in volume. Now, once again, that makes sense, doesn't it? If we're holding the pressure constant, which means we're holding the numbers of collisions constant, think bumper cars again. We're holding the numbers of collision constant. If we increase the speed and we want to keep the collisions the same amount, what are we going to have to do with the size of the bumper car ring? It's got to be bigger. So we're going to increase the volume, aren't we? If we are, once again, holding the speed constant, which is the temperature, we're holding the pressure constant, the number of collisions. If we decrease the speed to have the same number of collisions, what are we going to have to do with the size of the ring?
Shrink it.
Shrink it so that you have the same number of collisions. So we see that with increasing temperature, if we hold the pressure steady, we're going to have to increase the volume. And with decreasing temperature, you're going to have to decrease the volume. And so that's how we mathematically state Charles' law. So far, so good. Then it tells us, as soon as we have boiling water, we'll finish this experiment. Okay? So if you guys see this boiling before I do, just let me know, all right? Please turn to page 296. Now here we're told that when we apply this law, excuse me, we have a graph that shows us the volume on the y-axis and the temperature on the x-axis. Volume here and the temperature here. And if we hold the pressure constant on our experiments, we see that it continues down in a direction. As the temperature decreases, the volume decreases. And if you hold it at another constant pressure, you see the same basic thing. Okay. Now, honestly, it tells us that at negative 200 degrees Celsius, that's as far down as they can go, experimentally. I don't know about you, but I can't even imagine coming up with negative 200 degrees Celsius. But that's how far they've gone. And they've noticed this trend. And so what was interesting that they noticed is no matter where they held the pressure, these lines all seem to come together at one point. They would come to a zero volume at a particular point. And that particular point was negative 273.15 degrees Celsius. That was that zero point. Now, can you actually reach zero volume if you have matter involved? No, because by definition, matter has mass and takes up space. And volume is taking up space, isn't it? So you actually can't reach that temperature because then it would no longer have any volume to the gas. So that's impossible. But it's interesting that all of these experiments came back to this exact place. And so that place is called absolute zero because you actually can't reach it, because if you were able to reach it, then you'd have to make the volume disappear of actual matter. Does that make sense to everybody? Now, why is it important that we have a measurement that's based upon a scale that you can't reach zero? Eric? Oh, it's boiling. Okay, thank you. Let me finish this. The reason it's important that you have a scale that we use with gases that you can't reach zero is because you're not allowed to have a zero in the denominator, are you? Can we reach 0 degrees Celsius? Oh yeah, all the time, because it's just 32 degrees. They do it outside some places, right? And we can't have that. We can't have where we get a 0 in the denominator because then the algebra police will come take us away and act like the Gestapo, right? All right, you're not allowed to do that. I mean, it's been pounding in our heads all our lives. No zeros in the denominator. Correct? I mean, we don't even know what they'll do to us if we do that. It's just so bad. So, we have to use the Kelvin scale whenever we're dealing with gases. You must use the Kelvin scale when you're dealing with gases because you don't ever have to worry about having a 0 in the denominator because we're using the Kelvin scale. Now, thank you, Eric, for letting me know. So let's go back to our experiment. And we have boiling water. So it says, we did that once water's boiling. Carefully pour it into the glass until it reaches the level. Hold the plate in one hand, put the balloon in. Michelle, if you would be so kind, I need the balloon back. This is where I really make a mess. So I'm going to get a towel. I didn't bring a pot that had a spout, and I really should have, and it just didn't register. So I already did this yesterday, and I know what a mess I'm going to make. Because it just doesn't pour very well. Okay. All right, we are to the line. Does everybody see that? Here's our little freezer balloon. Everybody sees our little freezer balloon? And I've got our lid, and I'm going to drop it in and put the lid on. Wow. Can you see? Can you see how big the balloon's gotten? Seriously. Oh, the top's getting hot. Okay, I'm going to let her go, see what happens. Oh, it's got a seal going because it's a ball jar. See? Okay. You definitely can see that it's grown, right? Can everybody see that? Okay. And so I'm just going to put our little lid back here and unplug. Hang on. Charles' law, our balloonist, right? Charles' law. This one, now we're holding pressure constant, so we have V1 over T1 equals V2 over T2. Now let's apply this to our bumper cars. If we have pressure being held constant, our number of collisions is held constant. So if we increase let's say we increase the volume of our bumper cars, but we want the same number of collisions, and we increase the size of the rink, what are we going to have to do to the speed to keep the same number of collisions? You're going to have to speed it up. So as this, yeah, anyway, okay. So in other words, if the volume gets bigger, to keep the same number of collisions, the temperature has to get bigger, right? That makes them directly proportional, doesn't it? If the volume gets smaller, and you want the same number of collisions, your temperature would have to go down too. The speed of the bumper cars would have to go down, so you'd get less collisions, wouldn't it? Okay? So this one, it says that if the pressure is held constant, the temperature and volume are directly proportional. I guess the reason my brain wants to scream when I see that is when I think of inversely proportional, I think of a fraction, and in that one there's no fraction. And then here it says they're directly proportional, and here we have the fraction. And so my brain has trouble with the words. I'm okay with the math. I have trouble with the words. Okay, so forgive me for that. All right, so now, as you noticed, there is a little bit of a problem here. We have temperature in the denominator. And what do we use to measure temperature? A thermometer using Celsius, exactly. Can you get to 0 degrees Celsius? Oh, so easily. 32 degrees Fahrenheit, 0 degrees Celsius, too easy to get to 0, correct? And can we put a 0 in there? No, absolutely not. You cannot put a 0 in the denominator. The math police will come scoop you up and put you away. You know this, don't you? Yes, little car, woo, 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 and they'll just come grab you and put you away. Can't put 0 in the denominator. They get weird. So, I'm serious. Yeah, you can see that it's larger, right? It's definitely larger than it was. Oh, it's already shrinking because it's cooling off. Can you see that? Look at how fast it's shrinking because it's cooling off. Isn't that neat? It's supposed to get smaller in the freezer, and then it's supposed to expand in the hot water.